So we begin today's lecture with the importance of VC dimensions and especially we are going to talk about the structural risk minimization. So I trust that in our last lecture the actual concepts of VC dimension has gone into your mind properly. I mean, since we had discussed with a few typical examples, although they were very much oversimplified cases because we could consider only up to 2 dimensions. But I think with the examples of the quadratic argument of signum functions and the linear argument of signum functions, I think that some of the doubts that you were having earlier could be clear. So today we are going to talk mostly about the importance of VC dimensions, and especially the thing is that why do we need the study of this VC dimension? Because when we are trying to consider a neural network that can accept a set of training patterns, okay, then if the number of training patterns are fixed, all right, then the question is that what is the structure of the neural network that you are going to have, or rather in terms of VC dimension, what is the VC dimension that we have to choose so that the neural network gives the optimal performance. And this optimal performance actually should be in terms of its generalization capability, because in a neural network we are considering 2 types of error. Okay, number 1 is the training error, okay, which of course it's important to have a very low training error, because without having a low training error you cannot think of achieving high generalization, a good generalization capability. But even if the training error is low, okay, that doesn't necessarily guarantee that the generalization capability of that network is good. In other words, the generalization error characteristics, or rather the test error probability, something that we were discussing yesterday, okay, that has to be minimized, because only then we can say that the neural network is optimized in its performance, because ultimately it is in the test environment that we are going to use the network. So the thing is that by having an idea about the VC dimension, okay, it is possible for us to find out that where exactly is that condition of optimality coming in. The place of optimality is where the best kind of generalization capability exists, means in terms of the error there is somewhere a minima that we have to locate, okay, and VC dimension gives us some idea about that. Although one point should be kept in mind, that let us not be under the impression, since we discussed a few very simplified problems yesterday, okay, and there we could determine the VC dimension, which we showed that for the linear perceptron, we could see that if we have a dimension equal to 2, then the VC dimension of that becomes equal to 3. If it is m, it becomes m plus 1. Okay, let's not think that every time it will be possible for us to analytically calculate that what the exact VC dimension is. In fact, very often for the more involved neural networks, okay, which will involve a number of neurons and which will involve feed-forward connections between the neurons, or especially multi-layered neurons, okay, it is not always possible for us to, in fact, we should say that in general it is not possible to analytically determine the VC dimension, okay. Although the idea of VC dimension is still very important, because yesterday you remembered that the relation that I had shown, which was in fact suggested by Vapnik, that the relation that exists between the R test, the R training, and the expression that we had got, okay, in terms of the VC dimension, okay, VC dimension, then the number of training patterns. We had obtained that expression. In fact, we are going to present that once again today, because I mean most of our discussions for today will start with that expression. But before that, let us list out that what the importances of the VC dimensions are. Firstly is that it plays a central role in the statistical learning theory. Okay. In fact, that's what I mean our original discussion was. Okay, that we were in fact, I mean we are still deliberating on the chapter related to the learning theory, and towards the end of that chapter we discussed about the statistical learning theory. So this one plays a central role in the statistical learning theory, that is first importance of VC dimension. And the second factor is that the number of examples needed to learn a class is proportional to the VC dimension of the class. The number of examples needed so I mean, you know, in this case the number of examples needed, when I say number of examples needed, then I mean it is from the optimality consideration. Okay, ideally zero error, but since we will not be able to achieve zero error, at least we should go in for the minimum error criteria, okay, where the VC dimension plays a very important role. In fact, we are going to study about this aspect more, okay, and statistical learning theory, I mean more than what we have discussed, okay, I don't want to deliberate further because there are other topics related to neural networks which we need to cover in this I mean lecture series. Okay. Now in most of the cases, as I was telling you, that the VC dimension can be determined in terms of the free parameters of the network. Okay, like yesterday you had seen that for the example of two-dimensional cases and linear activations, okay, we had that I mean it is equal to the number of free parameters. In that case it was 2, okay, 2 plus 1, I mean in fact it was 3. Or to say that even if you take the case of a 2-input neural network, the number of free parameters are 3 because you have to include the bias. So it is indeed equal to the number of free parameters. So I can say that if W is the number of free parameters, then it is equal to, or it is of the order of W, okay. I mean for the simplest case it is equal to W, but I mean talking in terms of the order, it is order of W. I mean why I am talking of the order is because I mean ultimately we are going to talk in terms of the bounds, and there I mean for some typical neural networks, okay, for some typical activation functions, okay, we can determine that what those bounds are, okay. And in this case, okay, let me cite two very important results, okay, which has been reported by I mean the researchers in I mean literature, okay. And the two important results that must be stated is that firstly is related to the neurons with threshold activation functions, okay. So for neurons with threshold activation, so threshold activation we also describe that as the Heaviside function, okay. So as the Heaviside activation, I mean which of course is of the form phi v, okay, is equal to 1 when v is greater than or equal to 0, and this is equal to 0 otherwise, that means for v less than 0. So for such kind of neurons, that is with the threshold activations, okay, the VC dimension of this is, I mean it has been shown analytically okay, the VC dimension of this network is given by order of W log W, okay, where W is the number of free parameters. Okay. So, this is quite an important result, okay, that we can make use of. So, that means to say that with threshold activations, okay, it is of the order of W log W. Okay. So, this in fact is I mean happens to be better as compared to the I mean linear case, because in linear case it was simply order of W. Now, in this case in fact we have been considering okay, I mean threshold activation and also an arbitrary feed forward network. So, we are also considering a feed forward case, because this result is valid for the feed forward networks. Okay. And now another important result, okay, that we can say is when the activation function is sigmoidal. Okay. So, with sigmoidal activation function, with the activation function of this form, I mean which we had already discussed so many times earlier, 1 plus exponential to the power minus AV you say or minus V you say, it is all the same, I mean for sigmoidal case, and for the case of multi-layer feed forward network. I mean although we have not explicitly discussed multi-layered feed forward network, but I think you can guess that what I am talking of, essentially where we are cascading the layers of neurons simply. I mean you begin with an input layer, okay, and then all those input layers will be connected to some neurons, okay, which will be having activation functions, and those outputs in turn will be connected to another layer. Okay. So, if I have got two such layers, okay, I mean in fact including the input it will be 3, okay, then it is a multi-layered network. Okay. So, more than 2 layers, I mean from the input stage is a multi-layer, and if it is going only in the forward direction, okay, without considering any feedback connections between the neuron, means from the earlier layer to the I mean from the next layer to the previous layer, if such kind of feedback connections do not exist, then we should call those kind of networks as a feed forward network and of multi-layered type. So, for sigmoidal activation and with multi-layered feed forward, the VC dimension, okay, this is very interesting, VC dimension is order of W square, understand. So, this is, I mean this I mean obviously raises some interest. Okay. For linear activation we had W, alright. For threshold we had order of W log W, and with sigmoidal with multi-layered we are having order of W square. In fact, the tricks are being done by the multi-layered. Okay. Once we have a multi-layered feed forward connection, okay, then the VC dimension order increases, and this comes to our advantage, because one thing is very clear, that as we increase the VC dimension of the network, okay, its classification power naturally increases. Okay. So, definitely we should expect out of this, I mean we should expect a better performance, better classification performance out of a multi-layered feed forward network as compared to the single perceptron or single layer neurons obviously. Now, another interesting aspect that must be thought of, in fact this result of the sigmoidal activation function was pointed out by Koiran and Sontag. Okay. they are the people who had, I mean, in fact, all these theories are quite recent. In fact, Vapnik's theory itself is, I mean, published in the year 1992, and some further theories are published in the year 1998. And Koiden and Sontag also, I mean, quite recent results, I mean, over the past 6 or 7 years, I think. Okay, where Koiden and Sontag, they arrived at these VC dimension bounds by considering the multi-layered network in this way, that where they had, I mean, where they had shown two types. In a multi-layered feed-forward, they had shown two types of networks. Okay, number one, that they had showed the threshold functions, okay, and then they had shown sigmoidal function. Okay, and then, I mean, everything could be approximated. I mean, both threshold function as well as the sigmoidal function could be approximated using the linear activation. Because I think, I mean, this also is pretty clear in your mind, that if you are having a linear network with very high values of synaptic weights, okay, in that case, what it leads to? What is the limit if the weights are, I mean, increased? Threshold functions. It leads to threshold function in the limit, that when the weights are very high. On the other hand, when the weights are very small, then it could be approximated by the sigmoidal function. Or I mean, to put it in a bit of other way, I mean, for a sigmoidal activation with small synaptic weights could be modeled as a linear, and threshold functions could be modeled also as a linear but with high synaptic weights. So, because the linear model can be used, and we are using a cascaded version of that to form a multi-layered network, so that is why instead of order of W, we are getting order of W square. I mean, this is just to understand this realization of order of W square in a very simplified way. Okay, so the combination, so as we understand that the combination of two linears is giving us the order of W square, and in fact this is very interesting. Okay, now I mean, after talking about these two important results, okay, pertaining to the order of the VC dimensions, okay, let us go back again to the result that we had discussed yesterday from Vapnik's theory. Okay, so in fact we were discussing yesterday about the relation that should exist, or the inequality that should exist between R test and R train. Remember? Okay. In fact, I mean, yesterday as arguments I was putting alpha, where alpha vector was the free parameter vector, but I mean, it was pointed out to me that I mean, that will create some confusions, because so long, I mean, we should be consistent in the nomenclature, because so long we are considering always the W vector as the free parameter vector. So let us stick to the original nomenclature, and instead of using the alpha as the vector of free parameter, we take the original notation of W as the vector. So W vector, the free parameter vector, and again R train also will be in terms of the W vector. In fact, the relation that Vapnik had pointed out is that R test W, okay, should be less than or equal to square root of, in fact, because I am using R over here, okay, I don't want to use. No, here the free parameters are W only. Okay, we will not retain the alpha, because here I mean, since we are consistently talking about the free parameters as the W vector, the weight vectors, synaptic weight vectors. So it is the free parameter, and we will talk in terms of the W only. Since, I mean, that's what we all along understand by the free parameters, so I mean, no point in bringing the alpha. I mean, I am just writing a corrected nomenclature expression, so please make a note of it. H by, in fact here instead of talking about the R, because R is the error probability, or what we can call as the risk factor. Okay, so R stands basically for the risk, and because R is used for this, we will not use R for the number of training patterns. So instead we will use the number of training patterns as N. So N as the number of training patterns. So the expression that we are rewriting now is H by N, I mean everything under root, H by N log of 2N by H plus 1, okay, the square bracket closes here, minus 1 by N log, in fact I was yesterday telling it as eta by 4, again some confusion about our nomenclature, because eta was the learning rate. I mean, so long since we have been always using eta to be the learning rate, so let us not make that confusion, and I now substitute alpha is equal to eta by 4. Okay, so alpha in this case will mean, I mean, just a scalar quantity, just a constant quantity, which will be in I mean, which will be expressed as this eta by 4. So there we will be writing as 1 by N log of alpha. Okay, so this is the expression that Vapnik has pointed out. Okay, and in fact if you look at it, there are two terms in this expression. In fact, I mean this expression R train plus this whole thing together, okay, these two when summed up, okay, gives us some kind of a guaranteed risk factor, okay, for the test cases. I mean for the test patterns, the guaranteed risk function will be given by the summation of this. In fact it says it is less than or equal to, I mean it will be better than that, but at least it can never exceed R train plus this expression. Okay, so that way this bound has got a very significant purpose. So in fact we are going to call R guaranteed, okay, so let us call it as R guaranteed as a function of W will be equal to R train as a function of W plus this expression. In fact, I mean instead of writing this expression in terms of H, which is the VC dimension, N the training pattern, and alpha, so we are going to use a more simplified nomenclature. I mean we are going to call this as epsilon, which is expressible as a function of three things, N, H and alpha. Okay, where epsilon N H alpha is going to be this expression, that is H by N into log 2N by H plus 1 minus 1 by N log of alpha. All right. So this is what we are getting. So now definitely having defined the R guaranteed this way, R test is going to be less than or equal to R guaranteed. That is what it means. Now what is our variable? I mean since we are investigating with the effects of VC dimension, okay, let us now think of varying age. Okay, in fact I mean there are two terms here. One is the training error. So the first term is the training error, and the second term, this epsilon expression that we have got, okay, this is in fact referred to as the confidence interval. And why is it called as confidence? Because if you add the confidence to the training error, some confidence measure to the training error, then that tells you that what is going to be your bound on the test error. So at least if the confidence measure is known, you can confidently say that your test error is going to be less than this much. So that is why the name confidence measure or confidence interval that has originated. So two terms, the training error and the confidence interval. Okay. In fact both of these are definitely functions of age. Now, R train in the expression for the training error, we did not explicitly tell about any dependence on age, but if you think about it, very surely R train also will depend upon age. Isn't it very clear? You see, you take I mean a network, okay, or a two-dimensional network, let us say, okay, with two I mean synaptic weight connections, a single neuron, two synaptic weight connections, three free parameters. Your VC dimension is equal to 3 for that, okay. And now you take another network, okay, where you have 3 inputs, okay, 1 bias, so 4 free parameters. Here the VC dimension is 4. Now which one will lead to lesser training error? Obviously the one which is having more number of connections. So with age, with the increase of age, definitely that leads to a lowering of the training error. In fact, if we try to plot the training error versus the age, so on the x-axis if we plot age, so this is the increasing direction of age, and the y-axis we called as the error axis, where we are going to plot the error. So if we are plotting the I mean first term, that is the training error, then the training error will be of this nature, okay, something like an exponential. So this is the training error, or the R train expression, okay, R train as a function of W, right. Now this is the dependence of the training error on age. Definitely we all understand that as age increases, the training error definitely decreases. So that leads to thinking that definitely we should have as large an age as possible, okay. I mean as far as our budget permits, we should keep on increasing the age, we should keep on increasing the dimension of the network, and then we should have a better training error. But there is another factor, we have to consider the generalization aspect. Now just think that what is going to be this expression, what is going to be the dependence of the epsilon on age, does it increase or does it decrease, or unpredictable? Okay, definitely in this case n is much higher as compared to age, okay. That is bound to happen because you are considering n number of training patterns, so which will be much more than what the VC dimension tells you, okay. So definitely in this case what happens is that with the increase of age, okay, what happens is that this epsilon expression that monotonically increases, okay. So with the increase of age, epsilon monotonically increases. So the epsilon characteristic with age, or rather the confidence interval, should monotonically rise. In the case of training error it was monotonically decreasing, whereas in the case of confidence interval it should be monotonically increasing, something of this nature. Now comes the vital question, because not that we are very seriously bothered about the training error, not that we must reach exactly at this spot or at age tending to infinity. We are ultimately going to use the network where the test error is going to be minimized. Now what is the test error, or what is the R guaranteed? R guaranteed will be R train plus this epsilon. So this is epsilon in H alpha. So the addition of these two things, okay. And what kind of a characteristic would you expect for this R train plus epsilon, that is the guaranteed risk? Constant? No. I mean don't think that this epsilon is exactly balancing the training error. I mean it's not like an equalizer that it exactly balances. In fact, I mean if you calculate the characteristics, okay. Yes, there will be a minimum. In fact, the characteristic of the R test, okay, the risk on the test would be something of this nature. At a point it reaches the minima and then again it rises. Okay. So, this is something that we have to note. So, this is what? This is the R guaranteed, okay, or the yes, the limiting factor on R test. Now, R test is going to be better than this, but at least we know that in the worst case R test is going to be like this. So, this is R test W, okay, under the worst case. Yes? Yes, this is R guaranteed. So, I mean in the limit I say that this R test is equal to R guaranteed. Yes, I mean this is the limiting case of R test, or rather this is the R guaranteed. So, this is R test in the limit. So, the actual R test may be somewhere here, okay. It cannot go to this area, okay. It has to be lower than this. But definitely when we consider the bound, we have to be very careful about this characteristic, that at least this is the place where we find that there is a minima, and this is the minima that we should look for. Why? Because that gives the best generalization capability. So, the corresponding value of H, okay, should be somewhat the optimal value of the VC dimension, okay, which we must consider. If we consider unnecessarily a larger VC dimension, okay, we may feel happy that the training error is much less, but in the process of making the training error better, okay, we will be rather making the characteristic, okay, more vulnerable to the training error, to the test error. All right. So, in fact, this characteristic has got two very important regions to note. Okay. In fact, in this region, somebody can try to operate it in this region. Naturally, not very advisable, because here you are getting quite high training errors. Okay. You are also getting quite high test errors, but the test error is decreasing, but you are yet to reach the minimum. Okay. In fact, this is a region which we should call as the underdetermined, before the so this is underdetermined, okay, and beyond this minimum, okay, this leads, okay, let's not call underdetermined, the better term to say will be underfitment. So, here this is underfitment problem is happening in this region, okay, because as if to say that the network is inadequate, okay, the H is very low, and H very low means that the network is inadequate to learn these things, or rather to say that we haven't exploited the full capabilities of the network, whereas this one leads to the problem of overfitment. So, this is overfitment problem, okay. This one is underfitment problem, and here we have the point of minimum. So, we must look for the point of minimum, and how exactly are we going to do it? So, that is something that we should consider. Okay. Now, from the practical aspect, okay, really speaking, one has to experiment with it, right? If you ask me the question that from a practical point of view, how am I going to say that this is going to be the best type of H? Okay. So, in fact, we have to experiment upon, okay, and then come to a conclusion. So, in order to just make an expression of this, okay, let us say that we have got a nested structure of classifiers. By nested structure of classifiers, I mean to say that I am going to consider a classifier, okay, that can classify everything, okay. Then I am going to consider another classifier which is contained in that classifier, okay, but cannot classify everything that the earlier one could do, okay. And then another classifier which is contained in its previous one. Like that, I am considering a nested class of classifiers, okay. So I am going to just represent this nested class of classifiers as a set Fk, okay, where this set will be defined as the set of f x vector w vector. X vector w vector means it is neural network realization, x vector being the input, w vector being its free parameters, okay. And in this case, the w's that will lie in the region wk, okay. And here k will be 1, 2 up to n, okay. So that means to say that we are considering a nested structure of n pattern classifiers. Right, okay. And how we define the nesting? The nesting is done such that F1 is contained in F2, that is contained in F3, and so on, and the last class is Fn, which includes everything, okay. And if we are having this sort of nested pattern classifier, then correspondingly we must have H1 which is less than or equal to H2, less than or equal to H3 up to Hn, okay. Now what is the methodology that we have to follow for the structural risk minimization, okay. So if we consider a nested structure of pattern classifiers like this, then the method for structural risk minimization that we should follow is that the empirical risk means the training error. I mean, different books and literature, they call it sometimes as empirical risk, sometimes they call as training error, because training is after all an empirical data, okay. So that's why this is empirical risk or training error. So the empirical risk is minimized for each pattern, okay. And then you determine the pattern classifier, I mean out of all these pattern classifiers F1, F2 up to Fn, okay, you determine that which pattern classifier, okay, gives you the smallest guaranteed risk. Smallest guaranteed risk means this one. So in fact you are in this case, I mean I should say that could be that if I mean the set F1 will be here, then F1 will be contained in F2, will be contained in F3, etc., etc. Fn may lie, I mean somewhere over here. So there is a point of minimum, and let us call that as F star, okay. So the pattern classifier F star, okay, with smallest guaranteed risk, is identified. Okay. And in fact, I mean, that is the best solution that we are going to have. So, we are going to consider that pattern classifier which is having f star. I mean, f star will correspond to this point of minimum, all right. So, this principle actually is called as the structural risk minimization, okay. And this is where, I mean, you find that the VC dimension plays a very crucial role, all right. Now, practically how we are going to do, that is a question that we should address. See, I mean, normally a kind of analysis or the kind of this structural risk minimization is carried out for the case of multi-layered feed-forward networks, okay, which we will be learning in more details later on. Now, in a multi-layered network, typically the configuration is like this, that from the set of inputs, okay, supposing this is one layer, okay, let us say that we form an input layer, okay, and then, okay, so this is connected to one layer, and then these will be in turn connected to an output layer. Maybe that in the output layer we consider these neurons. Okay. So, these neurons will form the hidden layer, and this will be the output layer, and this will be the input layer. Now, naturally we normally do not want to touch the output layer, because output layer is finally going to give us the number of classes, all right. So, we in fact fiddle with the hidden layer, I mean, because hidden layer is not playing any direct role in generating the output. I mean, it is playing a crucial role, but somewhat indirect. I mean, even if we eliminate one hidden layer node, okay, it should be possible to still have a multi-layered feed-forward connection, okay. But whether that will have a better generalization or worse generalization is something that we should investigate, okay. So, we can have, let us say, a large number of hidden layer neurons to begin with, and large number of hidden neurons means that the VC dimension also will be correspondingly higher, okay. And we keep on eliminating each hidden layer neuron one by one, decreasing the VC dimension, okay. At one point we will be finding that the training error is minimized, okay, and that is the point, okay, that we have to note. Beyond that, if we keep on reducing the hidden layer nodes, okay, then it will again increase. So, that way we are going to find the point of optimality. So, that is one practical means of I mean, selecting the structure. So, this has got a, I mean, this VC dimension has got a very big impact on the structural design of the neural networks. I mean, is there any question that I can answer related to the VC dimension and structural risk minimization? Okay, so we will be then meeting again, and then we will be discussing about the single layer perceptrons, and I mean, in fact, we already have some elementary idea about the single layer perceptrons, but we will go more in terms of its convergence aspect, because that is one point which is very important. So, we will be beginning with the single layer perceptron chapter, okay, in the coming lecture. Thank you very much.